Okay, guys, so we are continuing part 3. Here's the first set of big ideas. So first, referring to learning target number 5, the conditions are the random 10% and the normal or large counts conditions. The way we check random and 10% is the same. And actually, the way we check the large counts is very similar to confidence intervals. The only difference is that instead of using p hat, we actually have an assumption for p here, so we can use p, the population proportion. So then learning target number 6 is about calculating the standardized test statistic. Standardized, remember, indicating that z-score and the p-value that goes with it. So we have to sketch our normal curve. It has the mean and standard deviation for the sampling distribution of p hat. So here are those formulas again. The mean is just the population proportion. The standard deviation is that p times q divided by n, and then take the square root. So you have to sketch that picture. And then you calculate the test statistic, that z-score, by taking the statistic p hat minus the parameter p and dividing by the formula for standard deviation. All right, once you have that z-score, just like our normal calculations before, we use table A2 to give us that p-value, the probability value. Left areas are calculated the same way. We just look at the table. Right areas, we have to do 1 minus the left area given in the table. And then we actually can check with normal CDF, and I forgot to mention that on the previous part, so I'm going to go back real quick. And number 6, where we calculated the probability of an 80% shooter making that sample proportion of 0.64 or less, that was our p-value. We could have, instead of using table A, we could have calculated normal CDF, had a lower limit of negative 10,000, something big negative number, but then an upper limit of negative 2.83, right? That's what I marked. I'm sorry, that was our z-score that we calculated. This is 0.64, sorry, I shouldn't have pointed to the picture, but that's the z-score. With a mean of 0 and a standard deviation of 1, because this is the standard normal curve. And that would give us 0.0023. Okay, so notice the normal CDF calculation gave us the same value from the table, but I only want you to check using this because I really want you to make sure that we're clear using that picture what the probability is. Okay, so let's move on to the next part. This is another situation. This would have been a fun activity to do in class. I'm disappointed we didn't get to do it. But I'm going to explain what we would have done anyways. So many students claim that they can taste the different colors of Skittles. Today, we will conduct an experiment and perform a significance test to see if students really can taste the rainbow. So I would have given you guys each a scoop of Skittles, which would be our random sample, and let you work with a partner to see if you really can taste the different flavors, right? You would close your eyes, your partner would hand you a Skittle, let's say it's purple. You don't know that, you taste it, and if you say it's grape, then you guessed correctly. I guess you shouldn't say it's grape. If you guessed that it was purple because it tasted like grape, then that would be correct. But if your partner gave you a purple one and you guessed green because you thought it tasted like apple, then it would be incorrect. Okay, so we did this in my class last year. It was fun. So out of the total tastings that we did, this was in a small class, they got 31 correct out of 81 total tastings. Okay, 31 correct guesses. So this format right here is the way you should conduct your your hypotheses test. It looks pretty similar to the 4-step process for confidence intervals, but there are some differences. Now we state our hypotheses and significance level in addition to the parameter and statistic. So first of all, we have a parameter P, right? This is a proportion of correct out of the total. So this is my true proportion. And then the way to phrase this, I could say of correct Skittle identifications, but that's just a little bit long. So I'm going to say of correct guesses. But I really am talking about guessing the correct color of Skittles. And then my statistic is p hat equal to 31 out of 81. So let's calculate what that is as a decimal. 31 divided by 81. Okay, so I'm gonna have to round here. I'm just gonna say 0.38 for the purposes of writing it on my paper, but I'm remembering any time that I'm gonna use p hat later, I'll use the fraction so that I don't have any rounding error. Okay, but just for purposes of simplicity, I'm going to write 0.38 to give us an idea. Okay, 31 out of 81 is about 38%. So now my hypotheses, My null is that nothing has changed or that nothing is interesting, right? My alternative is what I'm actually trying to see if I can prove. So I really want to show, or I would like to see, if students can taste the rainbow. If they really can taste it, then they should do better than just guessing, right? Their true proportion should be better than whatever the proportion is for just guessing. So my null is going to be P that is equal to the proportion for just guessing. So we have to figure out what that is. Well, I believe there are 5 different Skittle colors if we're just looking at the regular Skittles. So just guessing, you're going to get about 1 out of 5 right. So that's a proportion of 0.2. So if my alternative is that you're better than guessing, then my alternative is that P is greater than 0.2. Right, think about this, at a 5-question test and a 5 answer choice, multiple choice question, and you're just guessing on the question, your probability of getting that question correct is 1 out of 5. It's the same thing here with the different Skittle options. And then it gives us a significance level of 5%. Often in your homework problems, they will say, conduct a significance test with this significance level. But in real life, you would have to choose this. And 5% is a pretty typical significance level to choose. Okay, so something new. The name of this procedure is a little bit different. Instead of a 1 sample Z interval, this is a 1 sample, oops, I don't need a hyphen there, 1 sample Z test, because it's not an interval, it's a test for P. So pretty straightforward. We have 1 sample, it's based on that test statistic of Z, it's a test, and it's for a proportion, so P. Okay, so now let's check the conditions. So number 1 is that we have a random sample. And we do. We have a random sample of 81 Skittles, right? I told you that when we did this last year, I just took a random sample from the bag to scoop them out. So number 2 is 10% condition. So is our sample size of 81 less than 1/10 of the whole population? So of all, what would the population be? Of all Skittles, right? And that's true as well. 81 is definitely less than 1/10 of all Skittles. And then the third condition is our normal or large counts. Well, really it's the normal condition, but I check it by looking at large counts to make sure that my number of successes and failures based on the assumed proportion is true. So let's see. What is N times P? That would be 81 times 0.2. So what is the number of successes if I'm just guessing? Right, 0.2 is my null value. Okay, so 0.2 times 81 is 16.2. Okay, so 16.2 is indeed greater than or equal to 5. And I have to check the N times Q, so 81 times 0.8. Right, Q would be 1 minus 0.2, which is 0.8. So 81 times 0.8, 64.8. Okay, and that is obviously greater than or equal to 5 as well. So that condition has been met. Okay, so all 3 conditions are met. We can move forward, with our significance test. So the general formula, like I said before, is the test statistic. That is equal to the statistic minus the parameter divided by the standard deviation. You should write that out every time because it will really help you remember it, okay? So test statistic is the statistic minus the parameter divided by the standard deviation. Now let's plug in. The specific formula would be Z, that's my test statistic, is equal to P hat, the statistic, minus the parameter P divided by the square root of P times Q divided by N. Okay, so that's my specific formula. Now I can plug in what I know that to be. But before I do that, I would like to draw my normal curve. And in order to do that, I need to calculate that standard deviation. So that's sigma sub P hat. So sigma sub P hat is equal to P times Q divided by N and take the square root. So I really have 0.2 times 0.8 divided by 81 and then take the square root. Okay, so second square root of 0.2 times 0.8 divided by 81. 0.0444. okay, 0.044. So I'm going to use this to make my picture of my normal curve over here. And I actually am gonna pause the video here so you don't have to watch me labeling the normal curve. But remember, I'm going to start with my mean, which is the parameter P in the middle, and then add the standard deviation 3 times and subtract the standard deviation 3 times to get these values.